Hello, everybody. My name is Rafał Bachos, and I am principal scientist here at Simulations Plus. Thank you very much for joining this session, and the session is about the Python module called ADMET Predictor. On your screen, you can see the Visual Studio Code, which is a well-known integrated development environment. The tutorial is going to be the interactive session where we together will be going through the pieces of Python code. All the files are available as a part of standard ADMET Predictor 12 deployment. So if you go to the app data space of your ADMET Predictor 12 release, then you will find the directory called PyADMET Predictor. And within this directory, you will find the wheel file containing the PyADMET Predictor module itself, the Jupyter notebook, as well as all the other files necessary to execute the tutorial. So before starting, you should first install PyADMET Predictor. You can use the wheel file provided with ADMET Predictor 12, or you can use the most recent version of PyADMET Predictor just by executing pip install PyADMET Predictor. Please consult the ADMET Predictor manual where you will find the chapter devoted to PyADMET Predictor. Besides PyADMET Predictor itself, we also need a couple of additional dependencies. They are provided in the requirements.txt file. And if you type pip install -r requirements.txt, then you will equip your Python ecosystem and all the necessary libraries for today's session. So the entire idea of PyADMET Predictor is to find a synergy between ADMET Predictor and the Python ecosystem. And today we will be going through a couple of use cases illustrating the capabilities of both ADMET Predictor and Python ecosystem. The first cell is just loading all the necessary modules into the memory. So you can see that we will be using pandas, numpy, scikit-learn, and the well-known library, cheminformatics library, rdkit, and of course PyADMET Predictor. In this particular case, we'll be using the PyADMET Predictor in the version 0.1.3. In this cell, we are just defining and loading the helper functions that will be used later on. And here we are loading into the memory the sample of molecular data. This is a little fraction of drugs compounds. Since we are using rdkit here, we can easily visualize the structure directly in the Jupyter notebook. And here the information in the tabulated form. So you can see that we have here as smiles in the raw form, the initial form of our smiles code, and the identifier. The first use case will be related to the smile standardization. So we'll be using the command line interface to execute the certain ADMET Predictor script responsible for turning the smiles codes from raw form into the standardized form. Before starting, it is necessary to inspect the content of these two files, which is the configuration and the script itself. So if you look into the config underscore standardize, then you will see that this is a very simple file containing only two information, which is the location of ADMET Predictor executable and the location of the script. Please adjust it if needed. Similarly, if you look into the script definition file, which is ms underscore transform underscore compounds.txt, then you will see that this is a standard ADMET Predictor script file, and the only place which requires your attention is the line defining the file path alias. So here you have to provide the information, the path to the directory containing all these relevant files. After doing this, you are ready to perform the calculation. So as you can see here on this illustration, we will just take the smiles codes in the raw form. We will use the command line interface and we will turn them into the cleaned standardized form. We are just executing these couple of lines. As you can see, the resulting content contains the two objects, which is a log content and moles_sta. The first one is the parsed log file. So here you can have a look at this. Always when you perform the ADMET predictor calculations in a batch mode, then there is, besides the result itself, there is also like the information about the technical side of the calculation embedded in the simple text file. Here you can see that we have not encountered any errors, but in case of problems, it's always wise to look into that file and to fix the problems. As a result, here we've got also the moles_sta. This is a Python list containing RDKit mole objects. Besides the molecular information itself, we also get the attributes, and the attributes are the smiles_row, which is the initial form of the smiles code, and the smiles, which is the final form of the smiles after the standardization. And of course, we have the identifier. We can extract the attribute information from the Python list by using this extract properties function. And here you have the final result of your standardization provided as pandas data frame, and it contains the standardized smiles and the identifier. Here we can visualize the result. So this is simply the beginning of that list, 12 molecules. Here you can see the structures as well as the identifiers. And since we are in the Python ecosystem and we use the RDKit library, we can try to apply some functionality from RDKit, for example, the pattern recognition. So we define here this pattern, and we are just searching our list of compounds for the compounds containing this motif, this molecular motif. And here we can see that there are some matches. There are some molecules containing this molecular motif. Now we'll switch to another use case, which is the properties calculation via RESTful API. So as you can see here, we will take our smiles in the standardized form. We will apply the RESTful API to get the ADMET predictor properties. And here again, you have to pay your attention of a couple of things. So first of all, since we are going to use the ADMET predictor service, you have to make sure that the ADMET predictor service is running, and you have to pay your attention on this file, config_rest.json. Here we have the basic information about the availability of your RESTful API, which is the protocol, the host, and the port. And please adjust this file if necessary. After doing this, we are ready to go. So here you can see that we will be calling the asynchronous function, which will provide the ADMET predictor properties. And here in the next cell, you can just see indeed we've got the data frame containing our molecules in rows. Of course, here we just visualize only the head of that data frame. Therefore, we have only 5 rows, but we have more than 400 columns. And in these columns, we have different properties from ADMET predictor. So here we have limited our calculation to the properties from the groups descriptors and physiochemical properties, which are reflected in the resulting data frame. Here we will do the same, but by using command line interface. So we will just take our smiles in the standardized form. We will apply the command line wrapper, and we will get the properties. So from the functional perspective, this is exactly the same calculation, but we are using a different interface. Instead of RESTful API, here we use the command line. And again, you can have a look at the content of your log file. We do not see any problems here, which means that the calculation went well. You can have a look at the molecule, the first molecule on the list. And finally, you can have a look at the properties. So again, we get these properties in the form of pandas data frame. Since we have these properties already in the memory, we can use some analytical capabilities of ADMET Predictor, and we can carry out some exploratory data analysis. So first we will make sure that we have our descriptors and physiochemical properties in the memory. This is exactly the case. And yeah, the first simple thing is the statistical description. So we can get the statistics, the basic statistics for all of our properties and descriptors like count, the mean value, standard deviation, the quartiles, etc. The other use case here is the dimensionality reduction. So you can see here the definition of scikit-learn pipeline, where we have standard scalar, principal component analysis, and stochastic neighbor embeddings. So the idea is to reduce the dimensionality to 2 in such a way that we can visualize our compounds on a plane. So we take the compounds, we apply the standard scaling, then we reduce the dimensionality to 16 in the first step with principal component analysis. And then we apply the stochastic neighbor embeddings dimensionality reduction with a final number of dimensions being 2. And this is applied to the properties and descriptor representation of our compounds calculated before with ADMET Predictor. So here is the calculation. You can see that the final data frame is very simple. We have just the index, which is the identifier of our compounds, and 2 components of our t-SNE projection. And of course, we can visualize that. So we can take our data frame and we can just plot the t-SNE representation of our compounds. And of course, the coordinates, the location of the compounds reflects the location of the compound in the chemical space, of course, within this approximation that we've made, which means the projection onto the t-SNE space. We can make a step forward. So we take our t-SNE projection. We again visualize the compound, but in addition, we take the octanol water partition coefficient, the property, and this property is reflected in the form of the color of these dots. So here we have a bit more information. So still we have the coordinates, the t-SNE coordinates of our compound reflecting the part of the chemical space occupied by this particular compound, and the color reflecting the value of S log P, which is the logarithm of water octanol partition coefficient. So here we switch to another use case, which is the generation of pKa images. So we will apply here the command line interface. We will take our input structures and we will create the pKa images. Again, make sure that these 2 files, the configuration file and the script itself, are appropriately adjusted to your paths, to your file system. After doing this, we are ready to go. As you can see here, as a result, we obtain 3 objects: the log content, the molecules, and the images. So we can inspect the log content. It looks good, so we do not encounter any issues here. And of course, after that, we can look at our pKa image where we have indeed our macro states and micro states. So you can just take this image and embed into the report. You can post-process this information, etc. Another use case is the HTPK calculation, high throughput pharmacokinetics. So here we will be using the RESTful API again. So we take our input structures defined in another file, and we will just consume particular RESTful endpoints to get finally the PK properties. Again, since we are going to use the ADMET Predictor service, make sure that the service is running and that the file config_rest.json is appropriately adjusted to your needs. So before doing the calculation, we can just have a look on the availability of different properties. So these are the PK properties available in ADMET Predictor 12. And here we have the analogous information associated with opt-dose. Here we are loading into the memory the JSON payload defining our PK calculations. And we can have a look at this. So we will be looking at 3 compounds. And for these compounds, we will be producing the CP curves within the HTPK module. And based on these curves, we will be extracting the pharmacokinetic properties. Again, we are calling the asynchronous function, and we are getting the results. Here we can have a look at this result. So, the properties are more or less readable, but if you go to this part, these are the CP curves, then you can see that this is like a serialized form, not really human readable. But we are in Python ecosystem, so you can just take these curves and you can extract, deserialize them and extract the relevant information. So here we have the CP curve for the first compound, for the second compound, and for the third compound. And of course, what we can do is we can just take all these 3 curves and we can project them onto the common time domain space in such a way that all these 3 curves can be visualized on the same plot. And here we switch to the next use case, which is the metabolite generation. Here we will be using the command line interface. So we will take the input structures and we will calculate the metabolites within the command line interface. Again, please inspect this configuration file and the script definition and adjust it to your needs. So the execution, here we are running the code. Again, as you can see, we've got 3 objects as a result. So first we are looking at the log content. All looks good, so we do not see any errors here. So here you can see the information, what has actually happened. So we've got a couple of compounds, and for each of these compounds, we've calculated some metabolites. You can have a closer look at the first one, which is this one. You can see the native compound and 2 metabolites. And of course, the most important part here is the visualization of the metabolites from ADMET Predictor. So we have intercepted all these pictures, and here we can embed them in Jupyter Notebook. And as before, you can, by using this functionality, you can create a very nice report. You can share that information with your collaborators and do many other things. So now we are switching to the final use case, which is the 3D geometry generation. So we will take our 2D input structures provided as smiles codes, and we will use appropriate ADMET Predictor script to turn them into the 3D just by using the command line interface. Again, please have a look into these files and make sure that all the paths are set up appropriately. We can launch this calculation. So we get 2 information, the log content and the molecules already containing the 3D information. And since we are in the Jupyter Notebook and in the Python ecosystem, we can use a nice library which allows for the inspection and visualization of this 3D geometry. So that was the last use case. I'm hoping it was useful, and I'm hoping you'll be using PyADMET Predictor. I'm really hoping that this tutorial illustrated the potential synergy between ADMET Predictor and Python ecosystem. Thank you very much for your attention.